So this is going back. Do you remember from back in your earlier mathematical careers how to find the inverse of a function or what an inverse of a function is? I'm going to assume, especially this early in the morning, the answer is no, or I just can't think that much yet. But the process for finding the inverse is to switch the variables and then solve for y. So if you just switch the x and the y, and then we add 2 to both sides, so it'll be x plus 2 equals 3y, and then divide everything by 3, x over 3 plus 2 over 3 equals y. And we can rewrite it the other way if it makes everybody feel better. Usually it does. People like seeing it in slope-intercept form. That is the inverse function of the original function. So again, typically I'm going to call this f of x instead of y, which means down here we're going to call it the inverse function. So instead of y, it's going to be like that. And that's what inverse function means, f to the negative 1. It does not mean 1 over f of x. I know we've done a lot with exponents, but that is not what it means. So be careful when you're doing inverse functions that you're not thinking, oh, it's 1 over. No. Inverse means that we just flip-flop the variables. If I were to do f of f to the negative 1 of x, so if I take f of the inverse of x, if I do it the right way, well, let's go ahead and do it quick. So if I take the inverse function, which is this, and I plug it in for x in the original equation back up here, and I work this through, so I will have 3 times, so this x over 3 plus 2 over 3, and then minus 2. So again, see what I just did there? I just took the inverse function that we just found. I'm going to put it back into the x of the original equation. So I'm taking f of the inverse of x. So replace the x with what that value is. Then I'm going to do distributive property. 3 times x over 3 is x. 3 times 2/3, the 3's reduce, plus 2, and then outside the parentheses I have minus 2, which will equal then just x, f of the inverse function of x. And that will be true for every function and its inverse. No matter what they are, if two functions are inverses of one another, then this is true. So if you ever have a question that asks, are these inverse functions, is f of x the inverse function of g of x? If you did f of g of x, or if you did g of f of x, and if they're inverses, your result will be x. And if you don't remember why, here's why. In a graph, if I have a function, well, let me draw this line. So this line right here is the line y equals x. Slope is 1, the y-intercept is 0. An inverse function is a reflection over that line. That's what an inverse function is. So if I had one equation that was like this, the reflection is, well, this point gets reflected over the line to right there. This point would go across to about there and get reflected. This point here gets reflected across that line to about right there. And then if I connect those points, that would be the inverse function. The blue and red lines would be inverse functions, and they would intersect on the line of on the line of reflection. So graphically, that's what it is. And that's why when you take f of g of x, and they are inverses, It just equals x because the line is y equals x. But moving on. That's the only thing we're going to spend with inverse functions. It's just going to be a pretty quick, simple little aspect. As we approach the final exam, it would simply be a question like, are f of x and g of x inverse functions? You'd have to remember to plug f of x into g of x or g of x into f of x, solve it out, and get x. All right. This is where we're going to spend a little bit more time today. Exponential growth and decay functions. This top one here, this is growth. And the bottom one is decay. And when we're looking at this equation, we'll just define some of these variables. So C is my original amount. It's what we're starting with, depending on the scenario. So if we're dealing with growth of money in a stock account or something like that, the original amount, that was the principal, that's how much you initially invested. If I'm dealing with population, if population is growing, it would obviously be this function up here. And wherever I start for population, that would be the C. In chemicals, things that have a half-life, or things that have other types of exponential decay, when you think of radioactive material, the amount I start with is this. All right? And then R is my rate. For growth, that's my rate of increase. For decay, it's my rate of decrease. So R is the rate, in this case, the bottom one, rate of decrease. And it's usually written as a percent. You know, this is going to diminish or decay or go down or reduce by, 3.5% or 3% or 2%, or maybe it's a large number. It's gonna drop by 12 or 15% annually. But these would then be the two functions. X is the unit of time. So some things might grow at a rate per day or per week or per year. And then just paying attention to the context of the question will depend on what X is. So if it's going up per days and they said, and a month later, you'd say, well, it depends on which month we're in, but that's, 30 days, 28, 30, 31, one of those options. If it's annually, which is a lot of things, then X would be the number of years that whatever is going to happen in context. And then Y is going to be my ending amount. If we know something, C, is increasing at some rate for X number of years, then those numbers all plug in to give me the Y value or the ending amount. So this is more of a generic form. We're going to actually look at this and we'll see it as other kind of functions, typically functions related to time. So this variable will become a T. R will stay R. Sometimes this C will be P, especially when we're talking about finances. It's your principal. That's how much you start with. And then this will be like capital A of T, the amount over time. So for example, we have this. I'm going to write my function as A of T equals P times 1 plus R to the T. And the reason why I'm doing 1 plus R, because I've already done this problem and looked at it, well, actually I wrote it, is because it says it's growth. The minute it says growth, I know I'm doing 1 plus. And then let's start looking at what these variables are. So I have 2,000. So 2,000 is my principal. That's how much I'm starting with. My 11%, that's my R. And my 9, that's my T, number of years. So when I plug this in, it says after 9 years, so it's going to be A of 9 equals my principal, 2,000, parentheses, 1 plus, we have to be careful. That's a percent, but I'm dealing with decimal numbers. I need to convert my percent to a decimal. 11% is 0.11, raised to the 9 power. And then following, as always, PERMDAS. Order of operations, A of 9 is equal to 2,000. Got to do what's inside the parentheses first. 1.11 to the 9th power. Then I need to take 1.11 to the 9th power, which I cannot do off the top of my head, so I got my handy-dandy calculator right here. It's good that you are verifying these numbers when we work through it so that you are also confident. So there it is, to the 9th. So that ends up being 2.558. So this number is 2.558036924, et cetera, et cetera. Take that times 2,000. And I have the amount after 9 years is equal to $5,116.07. Because we're dealing in dollars, we'll go to the nearest hundredth. Which is not too bad. You can see like that within 9 years, our investment has over doubled, which is a fantastic investment, an aggressive investment current time, like as we're working in life right now. You can get upwards of 11% in the market these days, but you'd have to be on a pretty aggressive stance at that, which also means when it goes down, it's going to go down by large amounts as well. But 11% isn't unrealistic. When you think about just a standard savings investment type of account, or what's considered like a safe investment, you're going to be getting 2.5 to 3.5% growth. So my ending amount was 5,116.0. So now, what if we're in a recession for the next 9 years after that? So we got to go back 7, which is now my beginning amount. 5,116.07 is my new principal. It's now what I'm starting with. Because it says, what if we're now in a recession for the next 9 years after that, where there is, oh, wow, that was a really poorly worded sentence on my part. So the next 9 years, it's going to be recession. So there's going to be 11% loss each year. What's our final amount? We're going to go with our equation, A of t equals P times 1 minus R to the t power. Plugging in values, A of 9 again, but now we are starting with, because we just had an investment that grew, and now it's going to shrink. 1 minus 0.11 raised to the 9th power. So this will be 5,116.07 times 0.89 to the 9th power. So 0.89 raised to the 9th power is, in my calculator, this number here to the 9th power is 0.350356 and a bunch more numbers. That times this, times 5,116.07. And some of you might be thinking, well, shouldn't it just be back to my original amount? It is not. We end up with $1,792 and rounding up 45 cents. Much like an investment, if you start with more, you're going to end with more. This time we're starting with more, and then we're ending with less because, again, our starting amount was more. The impact of your starting value is huge when you're compounding. That's like this. These are compounding type scenarios of exponential growth and exponential decay. So moving from exponentials, then we get into what are called logs or logarithms. The longer word is logarithm. logarithm. I'll usually just refer to them as logs. The reason why we go from exponents to logs is because they're inverse operations, which is where we started today. We started talking about inverse operations. Logs and exponents are inverses, which we'll see that's how we're going to solve these equations at the end, is if I take the log of an exponent, I can get rid of the log and then solve for an exponent. But all a logarithm is, if you've ever seen them in the past, a logarithm is just a different way of writing an exponent. So if I look at this first one, y equals 5 to the x. This is exponential form. The best way to remember, well, how do I know it's an exponential form? If x is in the exponent, then it's exponential. That's really what an exponential function is. Now, it might not be x, but whatever my variable is, but oftentimes you think, where's my x? My x or my variable, my independent variables in the exponent, it's exponential form. 5 is called the base. Going back to all of our principles and properties of exponents, same bases that multiply, we add, same bases that divide, we subtract exponents. So 5 is my base. So when I look at a logarithm, this number down here is also referred to as my base. So this is log base 5. And the way this translates to there is it's log base 5 of y equals x. So the exponent is what it will equal. So in this case, it equals y. In a logarithm, it'll equal x. And again, think through the inverses. We kind of switch the variables around and we solve for x and y. That's actually what would happen, but it's log base 5 of y equals x. So anytime the exponent is my variable, that's the thing I'm looking for, I'm going to use logarithms to get it out in front. So again, these are all just kind of the same thing. 0.89 to the x equals y. I would rewrite it as log base 0.89 of y equals x. And that's how we write it there. And that's how we would read it as well. Log base 0.89 of y equals x. Now, I'll also tell you, it's rare that we're going to use different logs of these different bases. We'll eventually get to what are called the standard and natural logs. Those will be the ones that we'll use most often. And then I can do it the other way around. 4 to the third power is 64. That would be the same way as saying log base 4 of 64 equals 3. All right. And when we get to these problems, oftentimes this will have like a little, here I can even do it right here. Let's just cover that up. Box. There we go. It'd be like, hey, simplify this. What you would be thinking is 4 to what power is 64? And that's how logarithms are like exponents. Well, I shouldn't say they're like exponents. Logarithm is a different method of writing down an exponent. So I would do this, if this were my problem, I'd say 4 to what power is 64? Or if this were just an x, it would be saying, okay, 4 to the x power is 64. And then you'd have to remember, do I know my powers, some of the more common ones? 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. Those are your most common cubes. So then you go, oh yeah, so x is 3, which is what we had over there. 4 cubed is 64. So doing it more, but doing it in the other direction. 5, base is 5. 5 to the second power is 25. So again, if I have it as a logarithm, I can rewrite it as a exponent. 2 to the 1/2 power is I'm missing something in that because it didn't come over when I copied my equation. Square root of 2. Square root of 2. The 1/2 power means square root. So 2 to the 1/2 power is the square root of 2, which is 2 to the 1/2 power is the square root of 2. So log base 2 of root 2 equals 1/2. Or what we're really saying, 2 to what power is the square root of 2? So if I do something like this, you're thinking 2 to what power is 4? Say, oh, well, 2 squared, so 2 to the 2 power. And that's the process of thinking through how we're going to be simplifying and then eventually solving logarithms. But before we do that, we have to learn more properties of logarithms. Oh, no, I got a couple examples here. 3 to what power is 9? Way to jump in there, everybody. 2. 2 to what power is 8? 3. 2 to what power is 1/8? Gets a little bit harder here, so you think 2 to what, and if it helps, put your variable there. 2 to x power equals 1/8. Well, 8 we know is 2 cubed. So how do we get that to be a 1/8? It needs to go to the other side of the fraction bar. Well, how did we do that with exponents? So it would be negative third. So 2 to the x equals 2 to the negative third. X is negative 3. So when we're looking at these, oftentimes this base will have some connection to the base of that number as we're simplifying. So if I have log base 3, probably going to be looking at numbers like 9, 27, 81, those kind of things. So here, solve for x, we have to think, well, how do we convert this into exponential form? And it's a matter of just practicing and knowing, well, this is my base, so it's going to be 5 to some power. And then we go, well, which one is it? It is 5 to the third power equals the x. So it's 5 to the third power equals x, or 125 equals x. In terms of these, it's going to be practice. Practice converting it from log to exponential, exponential to log. Now we've got some properties of logarithms. Log base anything, so b is any number. Log base b of something is 1. What does that equal to? It equals 0. How do I know? B to the 0 power is 1. Any number to the 0 power is 1. And if you wondered why, like why is it that b to the 0 is 1? If I have b to the 4th over b to the 4th, remember our properties of exponents, same bases and dividing, it would be b to the 4 minus 4, which is b to the 0. But then also remembering, dividing, anything divided by itself is always equal to 1. So b to the 0 is 1. Any number to the 0 is 1, except for 0 to the 0. Next property. Log base b of b to the x equals x. And here's where we're talking about their inverse functions. B to the x, so if I take log base b of b, so same bases, log base b of the base b, they are inverse functions. They would leave me with only x in the exponent. It equals x. But also you'd say, okay, b to the x power is equal to b to the x power. And if they have the same bases, then x would equal x. And then also because they're inverse functions, if I started with log base b of x, and I took b and I raised it to that power, the b to the log base b are inverse functions, that would also leave me with just x. We'll do a couple problems that show that property. But this will be our last slide of properties, and then we'll do some example problems. If I am taking the log of two numbers, or two variables, or two anythings, that are being multiplied, I can split it up into addition of the two things. And the reason why is related to this. When I had same bases and multiplied, I add the exponents. When I'm taking log and I'm multiplying, I can split it up as adding. If I have two logs that are the same base, and I'm adding these two things whole together, I can then put them together into multiply. So you can do it in either direction. The log of two things divided is them subtracted. Just like we did on the last page. B to the 4 over B to the 4 is B to the 4 minus 4. And then last thing, and this is the one that we often forget and is one of the more valuable parts. So these we'll get the hang of. This one you just have to, at this point, almost memorize. But this is, I would say, the more valuable, the one that we're going to use more often. If I have the log of some base of a number to a power, that power can move, if you will. The mathematical property is it can come out in front and be B out in front. So if I have something like log base 5 of 3 to the x power, that can be rewritten as x times log base 5 of 3. The advantage is now my variable is out in front, and I can do some adding, subtracting, multiplying, dividing, the things like we used to do back in algebra. And this, although it doesn't look like it, is just a number that we will do in our calculators, and I'll show you how to do that. So now to practice these properties. When doing them, the first thing first, I have to make sure I have them as the same base. And luckily they are. They're both base 6. Since they're both base 6, I can use my properties of logarithms. I'm going to start with thinking about, it's not too dissimilar. I don't have necessarily parentheses, but I do have exponents going on. And this is remembering the last property that we just talked about. This first one here can be rewritten as log base 6 of 3 squared. Right? And the last one I said if the exponent is on the equation, it can come, or on the value inside the logarithm, it can come out in front. Now we're actually going to bring it back and put it on there. So it's log base 6 of 3 squared, which will be log base 6 of 9. You can do the same thing with the other one. So we plus log base 6 of 2 cubed. So this would be plus log base 6 of 8. When I have two logs of the same base that are being multiplied, that means I can pull them together and I can take the log of the two items multiplied. So when they're added, the connection is multiplying. So this would be log base 6 of 9 times 8, which will be log base 6 of 72. The only thing left at this point would be asking myself, do I know off the top of my head 6 to a certain power that would equal 72? 6 squared is 36. 6 cubed is way bigger than that, so the answer is no. So at this point, I would be finished because the question says, write this as a single logarithm. There's my single logarithm. Every once in a while, we'll have problems. We'll do all this, and we'll be like, oh, log base 2 of 8. And we go, oh, well, log base 2 of 8 is 3 because 2 to the third power is 8. But in this case, we cannot do that. We would be done at this point when we wrote that as a single logarithm.
We're going to do the same thing here, writing them as the same logarithm. Are they same bases? Yes, they're all base 3. I can do them in whichever order I want. I'm going to take these two first because I remember that adding same base logs is the same as 18 times 2. Be minus log base 3 of 9. 18 times 2 is 36, so I'd have log base 3 of 36 minus log base 3 of 9. And since I'm subtracting, much like exponents, the subtraction of exponents meant I was dividing, so that's what this is. Log base 3 of 36 over 9, which would then be log base 3 of 4. All right, so to take this and convert it into a string of logarithm phrases, I usually would start by saying, well, I'm going to get the dividing out of the way. So this would be log of 5 times 7 minus the log base 4 of 4. So that dividing by 4 means it was the same log bases, but I was subtracting originally. And then the multiplying, I'm going to convert that into the adding. So log base 4 of 5 plus log base 4 of 7 minus log base 4 of 4. And at that point, you could be done unless you recognized, which is possible. So log base 4 of 5, we don't know what that is. 4 to what power is 5? Ugh, that's not an easy one to do. Log base 4 of 7, also, we don't know. But 4 to what power is 4? 1. 4 to the first power. So this value here equals 1 because, again, logarithms are exponents. You're thinking 4 to what power, unknown, is equal to 4? 4 to the first power is equal to 4. So in a case where it says to rewrite it as a string of logarithms, this would be sufficient, but if you recognize this here, that would be fantastic. How a problem like this might be slightly bigger and or more complicated would be if I had something like log base 3 of 54 and say, can I simplify this in any way? What I'm trying to think of is like, well, what does 54 multiply to, and is any of that base 3? So numbers that multiply to 54 would be like 27 times 2. And this number, if I split it up like that, log base 3 of 27 times 2, so that would be then log base 3 of 27 plus log base 3 of 2. 3 to what power is 27? 3 to the third power. 3, 9, 27. So you could get it into some smaller parts and pieces by splitting it up. So we went through relatively quickly today the idea of inverse functions, exponential functions, and a few of them on logarithms. Logarithm. All right. Don't be alarmed when it says 1 through 21 odd. It's just getting you in the habit of convert it from this form to that form, this form to that form. It's not really much problem solving involved. It's just getting in the habit of going, oh, if it's an exponent here, it's something else here. If this is going on here, then it's a little bit different that way.
All right, but we're going to finish with, go back to a of t equals to p times 1 plus r to the t power. All right, and if I start with the same amount that we started with originally, $2,000. You do an initial investment of $2,000, and let's go ahead and assume that you have an 11% annual rate. People right now, if you go out there online and look for these kind of things, are saying, well, how much would you need to have in your retirement if you wanted to retire comfortably at like 60 to 65 years old? In current dollars, the number that a lot of people are striving for is $1 million. Because then, not knowing how long you're going to live, obviously, after you're 60 or 65 years old, should, if you have no other income after that point, be sufficient amount to last you, because you're not going to be stopping, you're still going to be spending money every year, but you're still going to get probably a lower rate of interest at that point. You'll choose something that's a little bit more, a little less risky, a little more consistent. But the question is, if this was you, how long would it take you to get $1 million? So we would look at this, a scenario like this, and say, well, my ending amount is $1 million. This will equal my principal, 2,000, times 1 plus my rate, 0.11. But now I have this unknown time, because I don't know how long it will take me to get there. So we need to solve for t. Where do we start? I'm going to simplify what's inside the parentheses. But now I need to solve for t. Working it like algebra, we always work outside in. Away from the variable, the thing that's farthest away from the variable is the 2,000. What is the 2,000 doing? The 2,000 is multiplying. So I will divides both sides by 2,000. So let's see, 1 0, 2 zeros, 3 zeros get off of there, and then I have 1,000 divided by 2, so half of 1,000 is 500. That will equal 1.11 to the t power. Now, I don't know what I can do next, but my variable is in the exponent. How do we get variables out of exponents? This was that third property of logarithms that I said. This is arguably the most valuable property that we're going to talk about. It's the property that says if I have y equals log of b to the a power, that's the same as y equals a times log of b. So that's what I'm going to do. I'm going to take the log of both sides. The log of 500, that is a really messy 500. Let me do that better. I need to say something at this point. If no base is written, this is what your calculator has. If you ever looked at your calculator, it has a log, L-O-G. If there's no base written, it is base 10. Why base 10, you say? Well, because our European folks were smarter when they set up their number system as base 10. Because if you go base 10, you can do a lot more with it, right? Kilometers, meters, centimeters, it's all base 10. But it's base 10. So that's what your calculator has as a program stored inside of it. It's going to find that number for you. So your calculator, if you did this, and I would recommend you do that now, 500, and then if you're using your phones, you hit log. If you have an actual calculator, you're going to hit log parenthesis 500.
Your calculator is saying 10 to what power is 500? All right. And so 10 will be, and you're going to be surprised, like it's not that big of a number because, well, 10 squared is 100. So not much more than that is going to be 500. But if you do this in your calculators, I keep saying that because I'm waiting for people to actually do that in their calculators. If you're watching online, you've pulled out your calculator because you're frustrated that I'm not doing this. And you're going to put it in there, and then you're going to hit log. And depending on the phone, you might have it as a phone calculator. It might actually say log base 10 in your phone. Some of them will just say log. But if you do, we find that that number is 2.69897, and then a few zeros. How far should you go? Honestly, go a ways. Now on the other side, we have the log of 1.11 to the t power, which will equal, and this is where this property comes into play, that comes out in front. T times log of 1.11. And the log of 1.11 is an actual number. So I am going to take my 2.69897 and divide it by the 1.11. I'm going to take the log of that and then divide it by that. And my t equals 59.55. 59.55, what you say? We are operating in years. So if you took, at your young age, $2,000 right now, found some type of investment that could get you, on average, 11% over the next 59 and a half years, you would then have for yourself $1 million, which 59.55 years from now will not be worth the $1 million that you know it to be right now. Unless a lot of things happen crazy in our economy, it'll be worth a lot less than what it is, So if to survive off $1 million now is not going to be what you're going to need then. But this also assumes you're not going to do any other investing, which most of you will. But also 59 years from now, many of you will be, 78 or 79, hopefully already into retirement and not still needing to work to get yourself to where you need to be. But this is how you then use T to work yourself backwards. It becomes a much more sophisticated equation when you start adding in the fact that, well, I'm going to keep investing this much money every year on year. Interest rates will change year on year. So it's not quite as a consistent model as what we have right here, but you start to get a sense for how things can happen and how things can grow relatively quickly. 9.6 and 9.7, the last two sections of this chapter, will get more into solving problems like this with log base 10, and then we'll do what's called the natural log, which is log base E. E is a number very much like pi is a number. They're both irrational transcendental numbers is what they're called. E is Euler's constant, named after Euler, E-U-L-E-R. You don't need to remember that, just fun fact. Euler did a lot of work in, obviously, logarithms, exponential functions, and his name comes up in a lot of other areas of math and science. But there we go.